Hello, in this video we're going to cover Unit 8, Section 5, which is going to look at the net ionic equations. These are another way that we have to write a chemical reaction apart from our chemical formulas and word equations that we saw in prior sections. So let's take a look at them. So what exactly happens with net ionic equations? This is what we're going to learn. So with ionic compounds, and this is only going to really apply to ionic compounds and I should say also acids. So ionic compounds and acids are going to do this. So when an ionic compound is found in the solid state, it's found like we have it here on the left side. It's found as a chemical lattice. Let me get my pointer here. So it's found as a chemical lattice, which we see here for sodium chloride in this case. This is a case that we studied earlier in earlier units for ionic compounds when they're a solid. But when an ionic compound dissolves in water, when it becomes aqueous, which we've been talking a lot about in this unit, Unit 8, it separates into its individual ions. Both ionic compounds and acids do this. So for example, if we were to put sodium chloride in water, if we were to dissolve the solid sodium chloride in water, whenever the sodium chloride touches the water, it's going to separate into our chloride ions for a Cl- and our sodium ions for the Na+. So if we look at here, this chlorine is going to go ahead and form Cl-, whereas the sodium in sodium chloride is going to separate out and create Na+ ions. So this process is called dissociation. It's the process of the separation of ionic compounds when they dissolve in water and acids into their respective ions. So if this was sodium nitrate, we will get sodium ions and nitrate ions. If there was sodium bromide, we will get sodium ions and bromide ions, so on and so forth. These ions are going to get surrounded by water molecules like we see here. So this happens to all ionic compounds and all acids when they dissolve in water. So whenever we write a formula equation or molecular equation like we've been doing, we haven't been showing the full picture. Why? When we write these equations, when we write these double and single replacement reactions mainly, we're showing every single one of these compounds that is aqueous as a full compound. So silver nitrate here is aqueous, but we show it as AgNO3. Sodium chloride, we show it as NaCl, even though it's aqueous. And we just discussed, these actually separate into ions. Remember that if you're in honors, we learn how to predict the products of single and double replacement reactions and then put in our states of matter according to our solubility rules. So these solids, aqueous, this all come from using the solubility rules as we learn in section 4 to determine which compounds are aqueous and which compounds are solid. We're going to keep doing this. So this, you can see this as an additional step to single and double replacement reactions from sections 3 and 4. We predict the products, we change into formulas, we put the states of matter on them, and we balance them. And once we do all of that, now we can start with creating what we call our net ionic equations. We can start creating an equation that actually shows these compounds not as a solid compound, but as separate ions when they are separate ions. So let's look at that. So we can write a new type of equation called a complete ionic equation. A complete ionic equation is going to represent ions or ionic compounds as ions if they are aqueous and they dissociate. So both acids and ionic compounds that are aqueous, so they have to be aqueous and they have to either be an acid or an ionic compound. in double and single replacement reactions are actually going to be represented as ions instead of the individual compounds. So, for example, earlier we saw that reaction, and let me write it on here. So earlier we saw that reaction that silver nitrate, AgNO3, aqueous, reacts with sodium chloride, NaCl, aqueous, to make silver nitrate, or silver chloride, AgCl, solid, plus sodium nitrate, NaNO3, aqueous. Well, what happens here? The compounds that we see here that are aqueous and ionic are actually not a compound. They're not a solid lattice like we saw earlier. Silver chloride, because silver chloride is solid, silver chloride will remain as a complete compound. But the other three, the sodium nitrate, the sodium chloride, and the silver nitrate are not going to stay as a solid compound. Whenever these reactions happen, those compounds, because they're aqueous and they're ionic, and this will happen with acids as well, are going to separate into their individual ions, meaning that this silver nitrate doesn't stay as aqueous silver nitrate. It actually separates because that compound dissociates into silver plus and NO3 minus aqueous. Sodium chloride, again, aqueous, and it's ionic, will dissociate into sodium ions and chloride ions. Silver chloride will stay AgCl solid because it's not aqueous. We only separate, in a complete ionic equation, we only separate aqueous ionic compounds or acids. Sodium nitrate, again, separates into sodium ions and nitrate ions because it's an aqueous ionic compound. So anything that's aqueous and ionic, or aqueous and an acid, for a complete ionic equation, we are going to separate it into its individual ions. Whereas if it's solid or not ionic, we are going to keep it together. This gives a better representation of what's actually going on in the solution, because those compounds that are aqueous actually dissociate. They actually separate when they're ions, and they don't stay as a solid lattice. So let's keep going here. The next step and the last step will be to show what we call a net ionic equation. For the net ionic equation, this is only going to include those compounds or those components that are actually undergoing a change. Why do we say that are actually undergoing a change? Well, if we look, if we look at this complete ionic equation that we have here in yellow, if we look at both sides of the equation, we are going to see that the nitrate ions, the NO3 aqueous, NO3 minus aqueous, and the NO3 minus aqueous on the other side, and let me clean this up so you can see that better. So that NO3 aqueous is both in the reactants and in the product side, and it's identical. It's NO3 minus aqueous on both sides. Same thing goes for sodium, Na plus aqueous, Na plus aqueous. While the complete ionic equation shows every single ion that is in that soup, in that solution, that aqueous water solution, it does have ions that don't actually do anything. The nitrate actually doesn't do anything, doesn't change from the reactants to the products. The sodium ion doesn't change from the reactants to the products. Whereas the silver ion and the chloride ion do react to come together and form the silver chloride solid. So those do react, whereas the nitrate and the sodium don't. This is why when we look at what we call the net ionic equation, the net ionic equation is that exact equation we had earlier, but without those ions that are identical on both sides. We call ions that are identical on both sides spectator ions. Spectator ions are ions that don't actually serve any purpose. They're just there to bring in the ions that are actually reacting. So the silver, for example, the silver ion wouldn't be able to be here without the nitrate ion, because we can just have a bottle of silver ions. We will need an anion in an ionic compound to bring it in. So that's what the nitrate is for. So we call the nitrate a spectator ion. They're ions that are not included in the net ionic equation because they do not actually directly participate in the reaction. The two ions in this reaction that are actually reacting with each other are the silver ion and the chloride ion to make the silver chloride. This is also why we need a solid in a double replacement reaction for the reaction to actually happen, because otherwise everything's a spectator ion. In this particular case of the reaction we've been following here, the sodium ion and the nitrate ion are those spectator ions. Because if we go back, the sodium ion and the nitrate ion are the ones that are going to be identical in the reactants and products section of the reaction, where the chloride and the silver are actually doing something. They're actually participating in that reaction. They're actually reacting, essentially. So the nitrate and the sodium here are the spectator ions. The silver and the chloride are the reaction. The ions are actually reacting. So let's look at some examples. This again can happen in both double and single replacement reactions, which is why we started asking you to put the states of matter on single replacement reactions in section 4. Because once we start doing that, we can then write a complete and a net ionic equation for a single replacement reaction. So let's say we have this reaction. We have lithium reacting with sodium hydroxide. Well, we identify this as a single replacement reaction, and we can see that the lithium and the sodium are going to swap places, so that the sodium is going to be by itself, the lithium is going to be with a hydroxide. And remember that we do need to check the activity series for this. So we need to make sure that lithium is higher than sodium, which it actually is. So once that happens, we can see that sodium and lithium are switch places, and we're going to end up with sodium plus lithium hydroxide. Oh, actually, I think I have enough space there. Sodium and lithium hydroxide. Oops. So we have sodium and lithium hydroxides. When we put this into a formula equation, we're going to end up with Li solid, because lithium is a solid as an element, plus sodium hydroxide, which is NaOH according to unit 6. So sodium hydroxide. Now, when we check the solubility rules, we can see that sodium hydroxide is going to be aqueous. I'm not going to do it here because we learned how to do this already in unit 4. But you should, if you don't know why sodium hydroxide is aqueous here, go back and review looking at the solubility rules for unit 4. So here's sodium hydroxide is aqueous. Then we have sodium by itself, which is a solid because it's a metal. And then lithium hydroxide, which is also aqueous, and we can see it here in the reactants. This is what we've been writing up to now, which is what we call the formula equation. This is already balanced. There just needs ones in front of everything. But once we have this formula equation, this would have been the end of, or the final answer for something like section 3. But now we can actually go further. We can put in or write out the complete and net ionic equation for this compound. Remember, to write the complete ionic equation, what are we going to do? We're going to find everything that is aqueous, or that is aqueous and anionic or acid. So we have aqueous here, aqueous is here, lithium hydroxide is ionic, sodium hydroxide is ionic. And we are going to separate those. So when we write the complete ionic equation, the lithium stays the same because the lithium is not aqueous and it's also not ionic. So lithium here is going to stay solid. So write as LiS. We're not going to change anything about it. Because sodium hydroxide is aqueous and it's ionic, we are going to separate that sodium hydroxide into the ions that make up the sodium hydroxide. So in this case, those ions are the sodium ion, which is going to become Na plus aqueous, and the hydroxide ion, which is going to become OH minus aqueous. On the other side, we have lithium hydroxide, which is aqueous and ionic. So again, because lithium hydroxide is both aqueous and ionic, we are going to separate it. If it was aqueous and an acid, we will also separate it. So how do we do that? We are going to grab the lithium, and that lithium is going to become the lithium ion, which is Li plus, aqueous, and we're going to keep that aqueous for all of these. Anything we separate has to be aqueous. And the hydroxide is going to separate into the OH minus aqueous. Sodium, because it's solid, is going to stay Na solid. So we're not going to separate the sodium. We're not going to put a charge on it. We're going to rewrite it exactly how it is. And then finally, the last step is going to be to write our net ionic equation. The net ionic equation is simply the complete ionic equation, but we are going to grab everything that is the same on the reactants and product side, and we are going to erase it. So let me erase these. So when I grab our now that we have our complete ionic equation to write the net ionic equation, we are going to grab this, and anything that's identical on both sides, we're going to cross out. In this case, the hydroxide, the OH minus aqueous, is identical. We have OH minus aqueous in the reactant side. We have OH minus aqueous in the product side. So that's going to get canceled out. Those are spectator ions. So that hydroxide is a spectator ion. The OH minus is a spectator ion. The lithium and the sodium, we are going to keep. Why? They're not identical. If we look at the lithium and the sodium, if we look very closely, let me change colors here. The lithium on the left side is Li solid. The lithium on the product side, on the right side, is Li plus aqueous. These are not the same. So the lithium changes. Even though it's still by itself, it goes from being an atom of lithium to being an ion of lithium, Li plus, and the state of matter also changes. The same thing happens with the sodium. It goes from being an ion, Na plus aqueous, to being a solid, Na solid. So we're going to keep, for the net ionic equation, we are going to keep the sodium, we're going to keep the lithium, but we're going to get rid of the hydroxide ion. So if we do that, then our net ionic equation is going to end up being Li solid plus Na plus aqueous yields Li plus aqueous plus Na solid. So you see how we're just rewriting the complete ionic equation without the hydroxide ion. So this part is actually very simple. All we're doing is looking at the reactants, looking at the products in the complete ionic equation, finding the things that are exactly the same, identical to each other, and we're just going to take them out to write the net ionic equation. The hardest part of all this process is the part from section 4 and 3, which is predicting the products, putting the states of matter, and balancing the equation. Everything new, the complete ionic equation and the net ionic equation, is just a matter of identifying what's aqueous, an ionic, or an acid, separating into its ions, and then canceling out the ions that repeat on both the reactants and the product side. So let's look at an example. This one's a double replacement reaction. So when we have the net ionic equation for the following reaction, cobalt 2 chloride reacting with sodium hydroxide. When this double replacement reaction happens, we are going to get a swap of the cobalt 2 with the sodium. So sodium and cobalt are going to swap places. Actually, I don't need the second one. So they're going to swap places. And we're going to end up with, in our products, cobalt 2 hydroxide plus sodium chloride. So when we do this for the formula equation, we're just going to translate this into into formula equation and write the states of matter. We get that cobalt 2 chloride is COCl2 aqueous because we check the states of matter. Sodium hydroxide is NaOH aqueous. Cobalt 2 hydroxide is going to be COOH2 solid. And sodium chloride is going to be NaCl aqueous. If this part confuses you, then this is not the video you should be watching. If this part confuses you, you need to go back to sections 2, 3, and 4 and review predicting products and assigning states of matter. Apart from that, we're also going to balance this reaction because every formula equation we need to balance. So that sodium chloride needs a 2 coefficient, that sodium hydroxide needs a 2 coefficient. So everything we've done up to now is sections essentially 1 through 4. We end up with what would be our answer for sections 1 through 4. But now we need to go a step further. Because these are double and single replacement reactions, and because we're going to be asked to do this, we are going to write a complete and net ionic equation which show what is actually happening in this reaction a lot more accurately. Because remember, this sodium hydroxide right here that is aqueous is not actually a lattice of sodium hydroxide. It separates sodium and hydroxide ions floating around in the water. So we're going to write our complete ionic equation. So there's a few things that we need to keep in mind here. For the COCl2, the cobalt 2 chloride, that 2 that we have on the chlorine is actually not part of the ion. What that's telling us is that we have 2 of the Cl minus ion. So we need to keep that in mind when we write our complete ionic equation because we're going to have to write 2 Cl minuses instead of 1. Same thing with coefficients. When we have something like the 2 in front of the sodium chloride, we mean that we have twice as much NaCl. So when we separated the sodium ion and the chloride ion, both get that 2 in front of them. So that 2 is going to be distributed. So the sodium is going to be 2 Na plus aqueous, not 1. And then the chlorine is also going to be 2 Cl minus aqueous. Because if we have 2 NaCls, then we have 2 Nas and 2 Cls. So we need to keep that in mind when we have a coefficient in a formula equation. When we separate something like the sodium chloride, we need to apply that coefficient to both the ions that we're separating. Whereas if we have a subscript like this 2 in the COCl2, then we only apply that 2 to the ion that it's for, in this case, the chlorine. So when we write this complete ionic equation here, we are going to write CO2 plus aqueous, because again, this COCl2 here, actually let me use a different color, so yellow. The COCl2 here, because it's aqueous, we need to separate that. The NaOH is aqueous, so we need to separate that. We're going to leave the COOH2 alone because the COOH2 is solid. But the NaCl, again, also aqueous, so we need to separate it. So everything here that I highlighted in green, we're going to separate because they're aqueous. Whereas this cobalt 2 hydroxide, the COOH2, is solid, so it's going to stay together. So here we see that the COCl2 aqueous gets separated into CO2 plus aqueous, which is the ion of cobalt, plus 2 Cl minus aqueous. Again, that 2 coming from that subscript. The NaOH aqueous, the 2 NaOH aqueous, is going to get separated into 2 Na plus aqueous plus 2 OH minus aqueous. Because again, that 2 in front of the NaOH needs to be distributed to both the sodium and the hydroxide ions. So we're going to have 2Na plus aqueous and 2OH minus aqueous. And then on the other side, the COOH2 solid, because it's solid, it's going to stay together, a COOH2 solid here. Notice, we write it exactly how it is. We do not put charges. We do not separate things. We write it exactly how it is because it's solid. And then the sodium chloride, which is also aqueous, we're going to separate into 2Na plus and 2Cl minus because of that coefficient. That gets distributed to both. So now we have our complete ionic equation. Great. This shows us all of the different ions or solids that are floating around in our solution. Now, to write the net ionic equation, we need to cancel out the spectator ions that are in this complete ionic equation. It's not fit. So the spectator ions that are in this equation are going to be the ones that are identical both sides. If we take a look, the chlorine is 2Cl minus aqueous in the reactants and 2Cl minus aqueous in the products. The sodium is 2Na plus aqueous in the reactants and 2Na plus aqueous in the products. So both the chlorine and the sodium are spectator ions. They need to be canceled out. Where the cobalt and the hydroxide, the CO2 plus and the OH minus are not the same in the product side. They're COOH2 solid. So those are going to stay in our net ionic equation, giving us CO2 plus aqueous plus 2OH minus aqueous yields COOH2 solid, and that's going to be our product. So that is going to be our net ionic equation once we completely cancel out our spectator ions. And that's our final answer now. This gives us a much better idea of what's actually happening in the reaction. The chloride and the sodium ions are just there for carrying in the cobalt and the hydroxide. The cobalt and the hydroxide are the two things that are actually reacting with each other to give us COOH2 solid, whereas the chlorine and the sodium simply float around and are exactly the same in the product side. Now, this can also happen with neutralization reactions, because remember, neutralization reactions are a special kind of double replacement reaction where an acid, in this case hydrobromic acid, reacts with a base, barium hydroxide in this case. When this happens, a neutralization reaction is always going to give us the water as one of our products, as we talked about in section 4, and the ionic compound made from the cation of the base and the anion of the acid. So the bromine and the barium are going to carry the barium bromide, Br2 aqueous, which is going to be always aqueous, and then water because this is a neutralization reaction. So hydrobromic acid, HBr, reacting with BaOH2. Now again, this you should be able to get this far, the formula equation, by just knowing what we did in sections 1 through 4. But once you're here, we are going to do the exact same thing to get our complete ionic equation that we did earlier. Remember, in order for something to be split apart, it needs to be aqueous and either an ionic compound or an acid. Well, because of the level we're at with honors chemistry, reality being that basically everything we see that's aqueous in this class for a single and a double replacement reaction is going to be either an acid or an ionic compound. So for this class, obviously don't take this into more advanced topics, but for this class, if you see anything that's aqueous, we can automatically assign it to be split apart into its ions. So with our complete ionic equation here, we're going to split our HBr. We're going to split our BaOH2 because they're aqueous. We're going to split our BaBr2. But again, because it's a neutralization reaction, water is one of our products. The water is never going to be split because water is a liquid, not aqueous. Don't get those confused. Water is a liquid. Liquid is not the same as aqueous. So when we do this, when we do our complete ionic equation, we are going to split it apart. That HBr aqueous is going to split apart, and that 2 is going to be distributed to the hydrogen and to the bromine, which is why we end up with 2H plus aqueous and 2Br minus aqueous. In the barium hydroxide, the 2 on the hydroxide only gets given to the hydroxide ion, which is why the hydroxide here in the complete ionic equation is 2OH minus aqueous, but the barium is only 1. There is no coefficient, because that 2, since it's a subscript, not a coefficient, only goes to the hydroxide. On the other side, same thing with BaBr2. That 2 is only going to be given to the bromine, not to the barium. So notice, barium in the products is Ba2 plus, no coefficient, whereas the bromine is Br minus aqueous with a 2 in front of it. And finally, for our water, because water is a liquid, not a aqueous compound, we are going to leave the water exactly how it is, and we're going to essentially copy and paste. 2H2O liquid becomes 2H2O liquid in the complete ionic equation. It does not get separated. And then once we have that, we are going to, for our net ionic equation, cancel out anything that's identical on both sides, which in this case is going to be the Br minus, which 2Br minus aqueous on both sides, so that gets canceled, and the Ba2 plus, which is Ba2 plus aqueous on both sides. So both of those are going to get canceled. The hydroxide ions and the hydrogen ions do not get canceled. So we are going to write them into our net ionic equation, because remember, the net ionic equation is just going to be the things that we did not cancel out written in. So the water, the hydroxide, and the hydrogen with their coefficients and everything in front of them. So we're going to get 2H plus aqueous plus 2OH minus aqueous yields 2H2O liquid. And that's our net ionic equation. We are going to bring in everything that was not canceled out, everything that's not a spectator ion, into our final answer. So the OH, the H plus, and the H2O here. Now, that is essentially what net ionic and complete ionic equations are. And these are all due to, or what they're used for, is that they're going to show us what actually happens during a chemical reaction a lot more accurately. Because in neutralization reactions, the actual reaction happens between the hydrogen ions and the hydroxide ions that make water. The bromine here and the barium were simply necessary to carry in the hydrogen and the hydroxide. They're like the ride. They're like when your friend takes you to the movies. They don't need to be there for you to watch a movie, but they were the way that you got there. The barium and the bromine are the way that the hydroxide and the hydrogen got into this reaction. But they don't actually do anything, right? So this is also why for double replacement reactions, if we have everything aqueous, there's going to be no reaction. Because imagine if we have this reaction. Sodium nitrate reacts with potassium chloride. NaNO3, which is sodium nitrate, and it's aqueous because of the nitrate, reacts with KCl, which is potassium chloride. When that double replacement reaction happens, when the sodium and the potassium swap places, they create sodium chloride and potassium nitrate, which are also aqueous. So what's the problem here? Every single compound in this reaction is going to get split apart. The sodium nitrate is aqueous, the potassium chloride is aqueous, the sodium chloride is aqueous, and the potassium nitrate is aqueous. Meaning every single one of these compounds for the complete ionic equation is going to get split apart into its ions. So we're going to split the NaNO3 into sodium and nitrate, the KCl into potassium ion and chloride ion, the NaCl into our the NaCl into our sodium ion, Na plus, and chloride ion, Cl minus, and the KNO3, the potassium nitrate, into K plus and NO3 minus. But here's what happens. When everything's aqueous and everything gets divided up in a double replacement reaction, that means that the sodium gets canceled out as a spectator ion because they're identical. The nitrate is identical on both sides. The potassium is identical. The chlorine is identical. So there is no net equation. Nothing's actually happening. When we add the sodium nitrate to the potassium chloride and they split into their ions, they don't actually regroup together because in the products, nothing is solid, nothing comes together, and they stay in their ion form as Na plus, Cl minus, K plus, and NO3 minus. So what we're making when we mix these two together is just a soup of ions. Nothing actually reacts. And that's why we say there's no reaction when everything in the formula equation is aqueous in a double replacement reaction. All right. So that's just why the explanation as to why no reactions happen with double replacements when we have everything being aqueous, and one of the very useful ways that we use net ionic and complete ionic equations for this. That is it for this unit and for this section of the unit. So make sure that you go back. Again, you're not going to be able to do net and complete ionic equations if you cannot do this first part. If you cannot go from the word or formula reactants to then predicting the products, or depending if you're in regular, you might not have to do that, but to predicting the products, putting the states of matter on the reactants and the products, and balancing out the equation. If you cannot do that from sections 1 through 4, then you won't be able to get the complete ionic equation and then the net ionic equation either. All right. So make sure you study the prior sections, and that is it for this section. Thank you for watching.